Hello everybody and welcome to chapter 6.4 of Advanced Functions. Today we're continuing with exponential functions as well as logarithmic functions. So today we're going to be covering the Power Law of Logarithms. However, we're going to go more in depth and explore other formulas and other properties of logarithms. So at first, I want to discuss how the power law is derived and what it is, as well as the change of base formula and how it was derived. Then I want to talk about more on evaluating different types of logarithms, as well as then do our homework and look at a few examples. So let's get started. Exploring the power law. So when it comes to solving logarithms, we must learn a way to solve for unknown exponents. So the power law allows you to do this exact thing. This is what the power law looks like. It is saying that log of x to the base b, when it has an exponent of n, it can be rewritten as n times log of x to the base b. So we just took the exponent of x and put it in front of the log. That might sound really weird, and you might be wondering, hey, how did this occur? Well, this 5-step derivation will show you how we did that. So first, I want to start off by saying, hey, how about we declare that m is equals to log of x to the base of b. Well, when we do that, we can rewrite this equation here as b to the power of m is equals to x, right? Since we had this is m to the power of n is equals to x. So now that we have this, how about we raise it to the power of n on both sides? So when we do that, we get b to the power of m times n is equals to x to the power of n. Now from here, we can once again write this in logarithmic form, and so we get log of b of x to the power of n is equals to m times n. Lastly, we could substitute the value we declared for m into the equation, and so we get log of x to the base of b, x to the power of n to the base of b is equals to n times log of x to the base of b. So this derivation you have to know how to do. You also will have to know the next derivation we're going to explore. However, first I want to show you why this formula is extremely useful. So for example, we're given this awful looking thing over here. So what do we have? We have log of base 7 of the third root of 343. So let's think about how we can rewrite this. Well, the third root of something is simply that number to the power of 1 over 3. So that is what we wrote here. Then, using the newfound power law, we know that we could just take this exponent and put it in front of the logarithm. And so we get 1 over 3 log 7 of 343. Luckily for us, 343 is 7 to the power of 3. And so we get this over here. We know that if we have something of the same base together, the answer would simply be the exponent. And so we're getting a fat 3 in the brackets. Again, you could simply take this part and write an exponential form, which you would get 7 to the power of something is equals to 7 over 3, and so 3 is equals to that something. Lastly, since we have a 3 in this brackets and a 1 over 3 outside of it, we just multiply them together, and so we get our answer as 1. As you can see, that was really something we wouldn't expect, right? Like, this sounds super complicated, but when you evaluate it, it just equals to 1. Like, that's insane. This also helps you out just purely further your understanding of logarithms, which is always a good thing. Now, let's talk about the change of base formula. So sometimes when you're working with logarithms, you're gonna deal with some ugly bases and or just numbers you can't input into a calculator. For example, some of the old calculators your school may be using or calculators that you may find online cannot or do not possess the power to input the base. So they only have the common logarithm and other ones, but not the one with the changing base. So when that happens, we can use the change of base formula. The change of base formula states that we can transform any logarithm into another logarithm of a different base in the following format. So we took the base of our first logarithm and put it as our x value in the denominator, and then we took the x value and then put that in the x value of the numerator. So what this allows you to do is transform anything into anything else you want. So your textbook will rewrite expressions to the base of 10, sorry. So for example, log of b of x could be log of x divided by log of b. So the c value here would be 10. C could be any values besides, it has to be greater than 0. It has to, and it cannot equal to 1. Because again, we talked about logarithms of base 1 and logarithms of base 0. They don't really make sense in our mathematical perspective here, and so we will not be doing or dealing with those. So if you're wondering how we got to this point, how did we find this formula? Well, it is a little bit more work than the power law, but you can get it done. So for example, again, we're gonna let m equal to log of x to the base of b. We're gonna rewrite it in exponential form, and so we got b to the power of m is equals to x. Then we're gonna take the log of both sides. This is perfectly fine. It's the same as taking the exponent or putting an exponent in front of every part of the function or the equation. It doesn't change the x values. So here we took the log of both sides, and so we got log of base c of b to the power of m and log of base c of x. As you can see here, we have a power, and so we can actually rewrite it using our power law. Good thing we learned that, right? And when we use the power law, we get this expression here. From here on, we could actually substitute our log b and x value for m, and so we get this wonderful equation. It might seem complicated, but we're almost done. Lastly, we need to isolate for log of x of base b, so we divide both sides by log b of base c, and so our answer is as follows. As you can see, we got the exact same answer, and so our derivation was perfectly legit and fine and perfectly done. So with that information, we can now use the change of base formula for when we want to transform a logarithm of one base to a logarithm of another base. Lastly, I want to discuss more methods and more important concepts you have to know to evaluate logarithms. Some of these we already discussed from your homework, but I just want to make sure that you understand them to the fullest extent. So for example, let's look at this one here. You have to memorize all three, and I've provided proofs for all three just in case you were wondering. So the first one we have is log of 1 to the base b. We're saying that this will always equal to 0. Well, why is that the case? Well, we can rearrange this and write an exponential form. So we get b to the power of 0 is equals to 1. And so that always makes sense, right? Anything to the power of 0 will be 1 as long as it's not 0, which perfectly fits with our definition of b in the context of a logarithm. And so we have proven that this is correct simply using this fact here. The second one is a little bit more tricky, but not quite. So using the power law, we could put the x over here, right? And so we get x of log b of base b is equals to x. When we divide both sides by x, we're just left with this information here. Again, writing this in exponential form tells us that b to the power of 1 is equals to b, which is always true. So it's just like proving a trigonometric identity. We know that for all values of b, the statement will hold true. Therefore, this statement over here will hold true for any value of b. Lastly, we have this over here, which is not a logarithm technically. It's an exponential function to the power of a logarithmic function. However, that doesn't stop us from evaluating it. Also, just a little side note, I can't make the b be a subscript because it is already a superscript for this b over here. So you just have to deal with it. But essentially, I'm gonna let y equal to this exponent. So y is equals to log of x to the base of b. So then this expression here is actually equals to b to the power of y is equals to x. Rearranging this and rewriting in logarithmic form gets us that log of x of base b is equals to y. And we know what y equals to. It equals to log of x to the base of b. Therefore, this statement is always true because those parts are identical. Hence, the whole property holds true. So with these three properties and the two formulas we found before, we can now evaluate a lot of logarithms. We are no longer constrained by the fact we didn't know how to change bases. We're no longer constrained to when we have something to the power of something as our x value. And for that, we can now go on to the homework. So the homework for today is these questions here. They aren't too difficult, but I will show you some of them so we can go over them together. Okay, so let's look at some of the homework questions. First, I've assigned 1A and C. It is really simple. It's just applying the power law. So first of all, you would put a 3 here, and then you would evaluate log 2 of 16. So 2 goes into 16 4 times, and so we get 4 times 3, and our answer would be 12. We do the same kind of procedure here. This is of base 10. Remember, if we don't see a value, that means we're dealing with a base 10. So then how many times does 10 go into 100? It goes in 2 times. So then 2 times -4 is equals to -8. Therefore, our answer is -8. Our next question was to B and D. Again, we just need to identify the fact that when we have a root or a radical, that is a value to the power of a fraction. So the square root is something to the power of 1/2. The cube root is something to the power of 1/3. The fifth root is something to the power of 1/5. So knowing that fact, we can evaluate our logarithms. So again, we would write a square root as something to 243 to the power of 1/2. So we'd bring the 1/2 to this side. And then we just find out how many times or how many multiples of 3's we need to get into 243. And then times that by 1/2, which should get us the answer of 5/2. Next, we do the same thing for D, except here it's a little bit more complicated, but not that difficult. We can first of all write 16 as 4 to the power of 2, then the fifth root of something, it would be 4 to the power of 2 to the power of 1/5, and then that whole thing is to the power of 15. So when we have that, we simply just multiply the roots together. So we could get 2 times 15, which is 30, divided by 5, which is 6. So our answer would be log 4 of 4 to the power 6, which is 6. Again, it sounds complicated, but if you see the steps, you'll see how simple it is. Then I said 4, which is this long question here. However, it is still not extremely difficult. So what it's asking us is that an investment earns 7% interest compounded annually. The amount of A that is in the investment is worth a function of time, t in years, and is given by this equation here. It still has to use the equation to determine the value of the investment. So first we substitute 0 in for t and then evaluate. This would give us a value of 500 because anything to the power of 0 is 1. Next it's telling us 2 years. So then we substitute 2 into the equation and evaluate. Same thing goes for 4 years. Nothing difficult here. Then it is asking us how long will it take for the investment to double and how long would it take for the investment to triple. So what we have to understand here is that we can equate this portion here to 2, right? If this portion here is equals to 2, our investment would be 2 times 500, which would be double. So if 2 is equals to 1.07 to the power of t, we can then use a logarithm to solve for it. So at first, what you could try to do is take log of both sides. Or, so what you simply have is log of 1.07 of 2 is equals to t. Then you could apply your change of base formula, for example, to evaluate for t. Or if your calculator has the base option, you could evaluate it straight from there. So for example, let's do this on Desmos, and I'll show you just how simple it is. So again, we just said to double it, 2 has to equal to our part of the function, which has an exponent. So I'm going to let this equal to x. When we have that, we can immediately find an answer. But if we were doing this algebraically, it wouldn't be that simple. So what I'd recommend doing is then transforming this into a logarithmic function. So we would have log of base, this is our base, 1.07. And then over here would have our 2. This again gives us our immediate answer. However, if you cannot input the base over here, so you're stuck with only your common logarithm, so for example this button here, we would do the change of base, which tells us that our x value goes on top. So sorry, this should be 2. And then we divided by the log of the same base. However, our new value in the x value was our old base. So 1.07. As you can see, this gave us the same answer, and that is the same answer the graph gave us. Therefore, we did this correctly. If we were to do question B2, it's telling us to when it triples in value, it's also super simple. Instead of having a 2, we now have a 3, and it triples now at around 16 years. Let's see if that is correct. Yep, 16.2. 16.2. There you go. Super easy. Next, we have question 5a, c, and e. This is just telling you to essentially use your change of base formula to evaluate these kind of questions. As you can see, none of them go perfectly into anything here. That is why it's telling you to use change of base. Again, if you have a calculator that could evaluate something with a base, it's super simple. Just plug this into a calculator. For 6, it's asking us to write a single logarithm. So when you're looking at these, you should understand that this is our change of base again. So this would be our old base, and this was our old x value, so a would be log of 8 to the base of 5. And so you do that kind of procedure for every single question here. Then we're skipping all the way to question 11. And then it's asking us, does log of m of x and m log of x equal for some constant of m? Explain why or why not, use algebraic graphical reasoning, and support using examples. Well, immediately we can solve this question by just plugging in these two equations into a calculator. So what did we have? Log of x to the power of n. Log of x to the power of n. Next, it's telling us m log of x. Oh, sorry, I did the wrong question. M of x. There you go. And then the second was m log of x. Adding in the m slider, we get this equation here. And then the second equation is right there. So do we appear to be correct? Well, let's see what happens when we change the slider. Oh, that's unfortunate. They do equal for some point of m. Which point was that? That was for when m is equals to 1. Then we can say that it only works when m is equals to 1. Again, we just graphed a bunch of functions and we see that is the only time this occurs. For every other value, they have different graphs. Again, it makes sense why it's only when it equals to 1, because m times x when m is equals to 1 is the same as log of x, and m times log of x when m is equals to 1 is still the same as log of x. So both of those functions were just demonstrating log of x. For any other value, we know that this over here corresponds to log of x to the power of m, right? So again, let's hide that guy and let them play out. This over here is like a phantom graph of this, but that is purely because for only certain values will it make sense. But as you can see, if we were to bring this guy over, they still overlap. Next, for 12, it's asking us to prove or show that if this equals for some constant of n. Again, we can use a graphing calculator to check this. You can also do it algebraically and equate all of them. So this was log of x to the power of n. Let's hide these guys, we don't need them anymore. And then log all log of x to the power of n. Log of x to the power of n. There you go. We'll put both of those in. Let's see if it is true. Oh. As it goes out, this might be seizure warning. Let's try to slow it down. As you can see, they do not equal for all the values. Like, no, the only time it does equal is when n is equals to 1. Do we have a restraint for n cannot equals to 1? No, we don't. So that is again our answer. It all makes sense once more. Anything to the power of 1 would still be x. This is still log of x. Both of these functions are still representing log of x. Lastly, let's talk about our question 15, which is the last question for today. So question 15 is talking about a spacecraft and it has two different parts to it. Essentially, all we have to figure out is when the spacecraft's 1,000 kilometers from the space station, reverse thrusters must be applied to begin braking. The time t in hours required to reach a distance of d in kilometers from the space station while the thrusters are being fired can be modeled by this following function. The docking sequence can then be initialized once the aircraft is between 10 kilometers of the station's docking bay. How long after the reverse thrusters are fired should the docking procedure begin? Again, let's try to analyze what this question is asking of us. The docking station can only be, the docking sequence can only start when it is between 10 kilometers of the range of our station. So we can actually just substitute 10 for our d value and evaluate for t. Again, you could use either your change of base questions or just simply plug it into a calculator. Then it's asking us for the domain and range of the function and what these features represent. Well, when we're dealing with a logarithmic function, we know that d in this concern could be any real value. However, if it is equals to 0, that means we are already at the station, so that doesn't make much sense to us. But we could have a distance of 1,000 kilometers. So our d value could be between 0 and smaller or equal to 1,000 kilometers. Our range would be defined by our t value, and t could be any real number as long as t is greater than 0. Again, the reason for why that is, our d value could be increasing really slowly, which would increase our time by so much that we would probably reach infinity by some point. And so that is why that is the case. Hopefully you understand the concepts presented in this chapter, because that is all the homework for today. As you can see, we are almost done chapter 6. Tomorrow we'll be looking at chapter 6.5, and then after that we're gonna start looking at chapter 7, which is still a continuation of exponential and logarithmic functions. However, it's a lot more algebraically based and just more word problems, so that should be fun, right? Overall, I hope you enjoyed today's lesson. It probably is a little bit longer than our other ones in this chapter, just because we're actually covering a whole lot of new material. Again, if you have any questions, feel free to email me, and I will see you next time. Bye bye!